Welcome to another pre-calculus video. In this one, we're going to wrap up section 4.1, our first section in trig. This is the applications. It says here the radian measure formula, theta, angle theta, equals s divided by r, can be used to measure the arc length along a circle. So here in the box we have a definition of arc length, or how long. Imagine if we're going to take a chunk of a circle and straighten it out and measure it with a ruler. How long is that piece of the circle? So for a circle of radius r and central angle theta, a central angle theta intercepts an arc of length s given by this formula. S, arc length, is equal to the radius times angle theta. I'm going to highlight this part. Theta must be measured in radians. You can't do this in degrees. Angle theta must be in rads. Make note, if your radius is just 1, then s is going to be exactly equal to the angle theta. And the radian measure of theta equals the length of the arc. So just a simple formula to plug and chug with. Again, make sure your angle theta is in radians. So let's take this for a test drive. They don't even give us a setup. They just give us a picture here. And they want us to find S, this chunk of the circle's circumference. So we've got our new formula. Arc length equals radius times angle theta. Now our radius is 4. So I'm going to put 4 there in a set of parentheses, and here we need the angle, and the angle's 240, but it is in degrees. So we are going to have to convert to rads. Remember, in the last video we have our conversion formula. So the given angle is 240 degrees. We are going to multiply that by pi over 180 degrees. And then on the diagonal, the degrees, the units, are going to cancel. We can also cancel off a 0 there. So that's going to leave us with a 24 pi over 18. And then I see those are divisible by 6. If we divide the numerator by 6, that's a 4 with r pi. Denominator divided by 6 is 3. So there's our angle, 4 pi over 3. That goes in for angle theta. All right, all we got to do here is multiply straight across. So S, the length of the arc, is going to be 4 times 4 pi. That's 16 pi. Denominator 3 times 1 is 3. Now that doesn't make a whole lot of sense to me when I see the pi in there. In this case, we are talking about arc length, so let's get it as a decimal. So we're going to switch to approximate because we're going to round this off a little bit. 16 pi divided by 3 is 16.7552. And did they give us units? Because we found the length. No units. It could be inches or miles or feet. Since they didn't give us one to specify, I'm just going to write units. But that is some length. How long is the chunk of that circle? 16.75 units. All right. Let's see what the next example. We got a couple more formulas here. So, linear and angular speeds. Let's talk about linear speed. I'm just going to come down here and give a quick example. Let's say you hop on I-80 and you travel 200 miles. And that journey took you 4 hours. So our numerator is how far we traveled, some length. Our denominator is some units of time. If we divide 200 divided by 4, that is 50. And then it's units in the numerator, miles, per units in the denominator, hours. 50 miles per hour. That's how long it took you to travel that. 200 miles, if it was 4 hours, it was a 50 mile per hour journey. Let's go back up here. So linear speed, we're going to use this letter V. It's an italicized V for the speed. And our numerator is arc length. Like in my quick example, that was the 200 miles that you traveled. And you're going to divide that by the time. In that case, I used 4 hours. So here, arc length is S. We just saw that before. And time is just T. Now, a good thing to put in your notes here, too. This S, we just found that in the opening slide of this video. Oops, get back there. That S is the same thing as R times theta. So we could replace this S with R times theta and put that over time. It might be more useful depending on how the problem's worded to use this formula, R times theta over T. And then moreover, if theta is the angle measured in radians corresponding to the arc length s, then the angular speed, here that little sort of looks like a cursive W, an italicized W, that is the lower case Greek letter omega. So the speed at which the angle is changing of that particle is, here's our angular speed, omega is equal to the central angle divided by the amount of time it took. Sort of like up here when we were doing linear speed, we did the length of our journey divided by the time it took to accomplish the journey. Here, our numerator is going to be the angle, the entire angle's measure, and we're going to divide that by some time units to get some speed at which the angle is changing. Now I see a study tip down there. What's this? Linear speed measures how fast the particle moves. Angular speed measures how fast the angle is changing. By dividing the formula for arc length by t, so here's our arc length formula, S equals R times theta. By dividing both sides by t, we can establish a relationship between the linear speed and the angular speed. So if we divide both sides by t, so this S divided by t, well, that's our speed we just saw here. S divided by t is our linear speed, and that's equal to r, the radius of this circle, times the angular speed, omega. Okay, so we just saw some new formulas here. I'm sure we're going to take them for a test drive. And here's our first one, linear speed. We've got a clock here, non-digital. The second hand of a clock is 10.2 centimeters, so there it's marked in the picture. Find the linear speed of the tip of that second hand. Now think about it, if I make this picture a little bit bigger. Let's say we've got a ladybug, and the ladybug is hanging on to right here on the second hand. So when it travels, it's not going to travel very far because that's just a quick trip because it's so close to the center of that circle. But what if that same ladybug was out here on the tip of the second hand? In that same 1 minute, this ladybug is going to go all the way around a much farther journey. So if we're right at the tip of this second hand, we're going to find some linear speed, and that would change as we moved closer to the center. So let's see here. First, we need to find the distance around there. Oops. Well, if we use, remember I said to combine that, this S, make this S into its own R times theta and divide by T. So let's use that. So we're going to do, and we're finding linear speed, so we're going to use that little V. Linear speed is equal to R times theta divided by time. Okay, let's see here. The easy part is the radius, that is the 10.2 centimeters of our second hand. 10.2 is our radius. Now our angle, theta. What angle are we going to use? Remember, we're letting that second hand go all the way around. So in radians, how much is a trip around the circle? Well, that's going to be 2 pi. 2 pi. Now for time, let's see here, we could choose by the minute. How many laps around does the second hand make in a minute? Well, 1. Or we could find this linear speed per second. And let's do that. For our time units, let's use 60 seconds. Because remember, we're doing 1 trip around the circle, so that's 2 pi rads, and that trip is going to take 60 seconds. Okay, so here, if we just punch that into our calculator, we'll get our final answer, and that's going to be we're going to use approximate because we're rounding, 1.068. Now let's figure out our units. Our length in the numerator was centimeters. 10.2 centimeters. Down here, our time unit, since we chose 60, that is seconds. So when we do that division, it's going to be numerator pieces, per denominator pieces. 1.068 centimeters per second. And now here's another one. This one we're going to find angular speed. We're also going to do a linear speed, kind of similar to what we just saw in the clock face. But in this example, we've got the blades of a wind turbine. They are 116 feet long. I'm going to take a guess that's going to be a radius somewhere. The propeller rotates at 15 revolutions every minute. Part A, find angular speed in rads per minute. And then part B, the linear speed of the tip of the blade. So that part B is going to be similar to what we saw with the clock face, but here with the angular speed, that's going to be a little bit different. So let me back up, do a refresher on the formula. Angle speed is the central angle, theta, divided by time. So theta divided by time, angular speed, omega, equals theta divided by time. Well, here, the time part's easy because they tell us in the setup, rads per minute. So our time is just going to be a 1. So that makes it easy. Now here, we need our theta, our angle. Now think about this. They gave us this piece of information, 15 revolutions per minute. If we do 15 revolutions every minute, how many radians is one of those revolutions? Well, one trip around a circle is 2 pi radians. So if we multiply the 15 and the 2, we get 30 pi. 30 pi divided by 1, so that would just be 30 pi. Now what's our units going to be? Numerator is in radians. Our denominator, they specified they wanted it in minutes. So that's going to be rads per minute. Rads per min. Okay, and we're going to use that, 30 pi rads per min, in our next part, part B, for the linear speed. So linear speed, part B, that is the V equals S over T. And remember, we also called that R times theta over T. And here we go. We're going to use that R times theta over T. Our linear speed is going to be, remember the radius of our props here is 116 feet. And we're going to multiply that by angle theta, and we just found angle theta. That's our 30 pi. And then we're going to divide that by our time units. I guess we'll just stick with per minute and leave it as a 1. And if we pull out the old calculator and multiply the 116 by 30 pi, and I'm even, because we're talking a length here, I'd rather see the pi gone. We're going to multiply by the decimal of pi. So if we just punch that in our handy TI-30, we're going to get 10,933 feet per minute. And there's about 5,280 feet in 1 mile. So this, with the 116-foot blade length and the 15 RPM in 1 minute, if you're trying to hold on to the tip of that windmill blade, you would travel almost 2 miles in 1 minute. And is that the last example? We got some practice problems in the team huddle. Pause the video and try the problems on your own. And I do notice here that none of these are dealing with linear and angular speed. All of these are going to use the S equals R times theta in one way or another. So pause the video and try the problems. You didn't pause the video, did you? Okay, now the first one, it's all based on a picture, and it says find the angle in radians. So remember, our formula is S equals R times theta. Theta is our angle. Well, let's what they gave us. Well, that's 7. Since it's in the circle here, pretty obvious, that's the radius. So 7 goes in for R. We've got theta, that's what we're trying to solve for. So what's our S? Well, that's the arc length. They gave us the arc length of this one, 32. So if we want to get the angle by itself, we want to get theta alone, let's divide by 7. Theta equals 32 sevenths rads. And usually you have a pi in your angle when it's rads, but you don't have to. We could just divide that out and get a decimal. So there's our angle. That's the central angle in radians. Now 91 is just like 85, but 87 there. 87 gave you a pick. Here they're just giving it to you written out. Find the radian measure central angle of radius r that intercepts length s. So it's the same thing we just did. S equals r times theta. S is 25. R is 14.5 times theta. And then if we just divide that, theta equals 25 divided by 14.5. Now, if we do that division, we get theta equals 1.724. 1.724. Now, one way we could turn this into an angle, a radian angle with pi in it, is to divide this decimal by pi. And I'm just going to divide that by 3.14. And we could write this angle also as 0.549 pi radians. So here's our angle in rads without a pi. If we divide that decimal by pi, here's our answer with a pi in it. Now the last one, we're going to use the formula to find the arc length, and they gave us the angle. Let's see if you fell into the trap. And I guess I'll move these over. So S equals R times theta is our formula. This time we're looking for S, that's our unknown. Our radius is 3 meters, and angle theta is going to go in this set of parentheses. If you put in the 30, you've got the problem wrong. Remember, this angle must be in rads. So we're going to convert 30 degrees into radians by multiplying by pi over 180. So the pi's cancel, we can drop a 0, and we get 3 pi over 18. Divided numerator and denominator by 3, that is pi over 6. So our angle theta, is pi over 6. And now we can just multiply the 3 times pi over 6. Remember, that's a 3 over 1. So we're going to have a 3 pi in the numerator and a 6 in the denominator. And the 3/6, that's going to reduce to 1/2, or just pi over 2. Now, because, again, they're talking about the length of an arc, pi over 2 doesn't do much for me. If we punch on our calculator pi and then divide that by 2, we're going to round that off to approximately 1.571. 1.571. And did you have units in your answer? Here, they were asking for arc length, and they gave us our radiuses in meters, so this answer will be 1.571 meters. Okay, I think that's the end there. Look for the assignment on WebAssign, and next time we're in class, we will do some odd problems.